A star vanishes in a heartbeat, outshining entire galaxies. This is a short gamma-ray burst, the universe's most powerful and fleeting explosion. In mere seconds, these cosmic flashes release more energy than our Sun will in its entire lifetime, then disappear without a trace. They are profound mysteries written in light, and they challenge the very laws of physics as we know them. By the end of this, you will uncover 30 mind-bending secrets hidden within these brief blasts, from the creation of gold to the fate of spacetime itself. We will explore how a collision of dead stars can forge precious metals, and why some explosions seem to happen in the emptiness between galaxies. What do you think is the most astonishing thing the universe can hide in a single second? The very first mystery is also the most fundamental. What cosmic engine could possibly create such a blindingly intense flash in such a vanishingly short time? For short gamma-ray bursts, the leading suspect is a collision of unimaginable scale. Picture two city-sized spheres, each containing more mass than our entire Sun, spinning around each other hundreds of times every second. These are neutron stars, the collapsed cores of dead stars, so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Their dance is a slow gravitational death spiral. Over millions of years, they inch closer and closer until finally, in a final, violent embrace, they smash together. That collision is beyond catastrophic. It unleashes energies that warp the fabric of space itself. In most scenarios, the two neutron stars don't just merge, they are utterly destroyed, collapsing immediately into a newborn black hole. But in the chaos of that creation, something extraordinary happens. For a fleeting moment, the swirling wreckage of the stars forms a disk of superheated material around the black hole. From the poles of this monstrous infant, twin beams of particles are blasted out at nearly the speed of light. These are the relativistic jets. If one of those beams is pointed directly at Earth, we see it as the short, sharp spike of a gamma-ray burst. It is the dying scream of two dead stars, a final beacon announcing the birth of something even darker. This sets them completely apart from their longer cousins, the long gamma-ray bursts, which are thought to be the death throes of a single, massive star collapsing into a black hole. That process takes minutes, not seconds. The merger model explains the brevity perfectly. The fuel source, the swirling disk of star stuff, is used up incredibly fast, snuffing out the jets almost as soon as they ignite. So while a long burst is like a supernova in slow motion, a short burst is something else entirely. It is a hyper-violent, hyper-efficient detonation, a single, universe-shattering gunshot fired from the wreckage of a stellar collision. And that collision leaves behind more than just a black hole and a flash of light. It forges the very elements that make our world possible, a clue that leads us directly to the next profound mystery. That newborn black hole's violent birth is only the beginning of the story. The initial gamma-ray flash lasts mere seconds, but the true aftermath, the cosmic crime scene, should linger. This leads us directly to the second great mystery. Why are the afterglows of short gamma-ray bursts so incredibly faint and difficult to detect? For their longer cousins, the story continues in brilliant detail. A long burst's explosion is like a massive, ongoing fire, and it leaves behind a bright, slowly fading ember. Astronomers can watch this afterglow for days or even weeks as it shines in X-rays, visible light, and radio waves, painting a clear picture of where it happened and what surrounded it. But a short burst is different. It is a sudden, precise strike, like a lightning bolt in the cosmos. And just like lightning, once the brilliant flash is over, the darkness seems absolute. Often, there is no obvious afterglow at all, just a silent, empty patch of sky where the explosion occurred. When an afterglow is detected, it is typically a whisper, a faint and fading signal that vanishes within hours. This poses an immense challenge for the detectives of the cosmos. Imagine trying to solve a murder where the body and all the evidence vanish almost immediately. Without a bright, lingering afterglow, pinpointing the exact location of a short burst is extraordinarily difficult. You cannot easily trace it back to a specific galaxy to understand what kind of stellar neighborhood it came from. Was it in a young, star-forming galaxy or an old, quiet one? This context is crucial for testing our theories. Missions like Swift and Fermi are built for this high-stakes chase. The moment their sensors detect a gamma-ray flash, they spin with robotic urgency, aiming their telescopes at the patch of sky in a desperate race against time. They are searching for that fading X-ray or optical signal, the last dying echo of the collision. Catching it is a matter of minutes. Every second that passes means the signal grows exponentially weaker, slipping back into the eternal background noise of the universe. This faintness itself is a clue. It tells us that the environment around a short gamma-ray burst is remarkably clean. There simply isn't much material surrounding the collision to get heated up and glow for an extended period. It suggests these mergers happen in relatively empty space, far from the dense gas clouds where stars are born. But this clean environment creates another, even deeper puzzle. If two neutron stars are born from massive stars that lived and died together, why would they merge in such an empty place so far from their origins? The emptiness surrounding their final act is a clue to something far more precious. This brings us to the third and perhaps most glittering mystery of all. Short gamma-ray bursts are not just destroyers, they are creators on a cosmic scale. They are believed to be the universe's primary factories for the heaviest elements in existence, including gold, platinum, and uranium. Think about that for a moment. The gold in your jewelry or the platinum in a catalytic converter was not forged in the heart of a star like iron or carbon. It was born in the most violent conditions imaginable in the seconds following a stellar collision. The process is called the rapid neutron capture process, or the R process for short. During a neutron-star merger, a small but incredibly dense fraction of the star material is not swallowed by the new black hole. Instead, it is blasted out into space in powerful, neutron-rich winds. In this expanding cloud, atomic nuclei are bombarded by a staggering flood of free neutrons. They capture these neutrons faster than they can decay, building up atom by atom into heavier and heavier elements in a matter of seconds. It is a runaway nuclear assembly line operating at the edge of physics. But how do we know this actually happens? The proof is in a faint, radioactive glow called a kilonova. In 2017, astronomers witnessed history. For the first time, they detected both the gravitational waves and the gamma-ray burst from a neutron star merger. What followed was even more spectacular. Over the next days and weeks, telescopes saw a strange, fading light in that patch of sky. It started out blue and hot, then shifted to red. This was the kilonova, the signature of heavy elements decaying. The expanding cloud of newly forged gold, platinum, and other R-process elements was so hot from radioactivity that it glowed with its own light, painting the aftermath of the collision in colors that revealed its chemical composition. It was a direct confirmation that these mergers are cosmic alchemists, yet profound uncertainties remain. We still do not know exactly how much material is ejected in each merger or what precise cocktail of elements is created. Is every collision equally productive, or do some forge more gold than others? The conditions in those first chaotic moments, the temperature, the density, the neutron flux, are so extreme they cannot be replicated in any laboratory on Earth. We are left observing the aftermath, trying to decode the recipe from the final, cooling products. So the next time you hold something made of gold, remember its origin story. It is not just a metal, it is stardust of the most exotic kind, a relic from a cataclysm that briefly outshone galaxies and birthed a black hole, a literal piece of a mystery that lasted only seconds. But the creation of heavy elements is not the only secret these mergers hold. Their location in the cosmos tells a story of its own, and it is a deeply puzzling one. This is the fourth mystery, the lone wolf paradox. When astronomers finally manage to pinpoint the location of a short gamma-ray burst, they often point their most powerful optical telescopes there, expecting to find a host galaxy. After all, neutron stars are born from massive stars, and massive stars live in galaxies. Yet, in a significant number of cases, they find nothing. The explosion appears to have happened in the profound emptiness of intergalactic space, a lonely flash in the void with no visible galactic home. This is a paradox that strikes at the heart of our models. How can a pair of neutron stars, which must have formed within a galaxy, end up merging so far away from it? There are two compelling and violent explanations. The first involves a cosmic kick. When a massive star goes supernova to form a neutron star, the explosion is almost never perfectly symmetrical. It can be lopsided, like a rocket engine firing unevenly. This imbalance gives the newborn neutron star a tremendous kick, launching it out of its birthplace at speeds that can exceed 1,000,000 miles per hour. If the star was part of a binary pair, this kick can send the entire system, both stars, hurtling on a one-way trip out of their host galaxy. They become stellar exiles, wandering the dark intergalactic medium for billions of years until their eventual merger. The second possibility is even more dramatic. It suggests the binary neutron star system was not ejected alone, but was part of a dense, ancient globular cluster, a spherical swarm of millions of stars that orbits a galaxy like a distant satellite. In such a crowded environment, close gravitational encounters are common. A passing star could perturb the binary, tightening its orbit and drastically speeding up its merger timeline. The collision then happens right there in the cluster, which itself may be so faint and distant that it escapes detection, making the burst appear isolated. Or perhaps the host is not a grand spiral galaxy, but a tiny, ultra-faint dwarf galaxy, a wisp of stars so dim it simply blends into the cosmic background. Each scenario paints a different history of violence and exile. The lone wolf bursts are cosmic orphans, and their very existence forces us to rewrite the life story of these stellar binaries. They are not just products of their galaxy, but can be shaped by chaotic interactions and ejected into the great dark between the islands of light. This wandering nature leads directly to another, even more fundamental question about their timing. If they can be flung so far from home, how long does it take for their final dance to begin? The timing of their exile is just one layer of the mystery, because the final moments of the dance hold secrets of their own. This brings us to the fifth enigma, the precursor puzzle. For a handful of short gamma-ray bursts, the main event does not arrive without a warning. Seconds or even minutes before the colossal flash that outshines galaxies, satellites detect a faint, fleeting whisper of gamma rays. It is a ghostly prelude, a brief flicker in the darkness that vanishes almost as soon as it appears, only to be followed by the true cataclysm. What could possibly cause a signal like this, moments before two dead stars tear each other apart? These precursors are like the first tiny cracks in a dam just before it bursts, offering a direct glimpse into the instants before total annihilation. One leading theory is almost poetic in its violence. As the two neutron stars spiral closer in their final orbits, their immense gravitational fields pull on each other with unimaginable force. This tidal stretching could be so severe that it literally cracks the star's crusts. Neutron star crust is not like anything on Earth. It is a lattice of ultra-dense atomic nuclei, a solid shell over a sea of degenerate particles, and it is under immense strain. A global starquake triggered by the gravitational tide could release a sudden pulse of energy, a shiver of gamma rays sent out into the cosmos as a final distress signal before the structure fails completely. Another possibility points to the last gasps of the star's magnetic fields. As the stars get closer, their powerful magnetic fields begin to interact and tangle violently. This magnetic chaos could reconnect, snapping like over-tensioned rubber bands and accelerating particles in a brief pre-merger flare. Or perhaps the precursor is a sign of the first actual contact. Just before the full merger, the outer atmospheres of the two stars might begin to mingle and shock heat, producing a small flash as the final countdown truly begins. Detecting and studying these precursors is a monumental technical challenge. They are faint, they are fast, and by the time our instruments register the main burst, the precursor data is already ancient history buried in the data stream. But if we can catch them, they become a unique scientific tool. The timing and energy of that pre-flash could tell us about the strength of the neutron star crust, the configuration of their magnetic fields, and the exact dynamics of those last frantic orbits. They are a direct probe of the physics operating in an environment where gravity is so strong it warps time itself. So these mysterious flickers are not just cosmic static. They are the last telemetry from a doomed system, a final message sent an instant before two worlds end, and a new one is born from the wreckage. And that birth, the formation of the central engine itself, is shrouded in its own profound uncertainty. The physics of that newborn black hole offers a staggering clue to the next mystery. Where does the energy for a short gamma-ray burst actually come from? The numbers are almost impossible to comprehend. In a few seconds, a single burst can release more energy than our Sun will produce across its entire 10 billion-year lifetime. That is not just a big explosion, it is a fundamental violation of our everyday intuition about power. To generate that much light in that little time requires an engine of almost perfect efficiency, a cosmic power plant that operates at the very limits of what physics allows. So what is the fuel? The leading candidate is not mass but motion, specifically the spin of the newborn black hole. When two neutron stars merge, they don't just create a static pit in space-time. They create a whirlpool. The combined angular momentum of their final, frantic dance is transferred to the black hole, making it spin at a significant fraction of the speed of light. This rotation is an immense store of energy, a battery charged by the death spiral of two stars. According to Einstein's theory, we could, in principle, tap that rotational energy. The mechanism is thought to be the magnetic fields anchored in the swirling disk of leftover material. Think of it like a gigantic, natural dynamo. The incredibly fast spin of the black hole and its disk twists and amplifies these magnetic fields into coils of unimaginable power. These fields then act as conduits, channeling the rotational energy into those narrow, ultra-fast jets that become the gamma-ray burst. It is a process of direct conversion, turning the spin of a singularity into the most luminous light in the universe. But there is a crisis in this elegant model. The efficiency required is staggering. To produce the observed bursts, the engine must convert something like 10 to 50% of the available mass energy of the system directly into gamma rays. For comparison, our most efficient human-made process, nuclear fusion in a hydrogen bomb, converts less than 1% of mass into energy. This cosmic engine is dozens of times more efficient than a thermonuclear weapon. It pushes our understanding of plasma physics and magnetohydrodynamics into uncharted territory. We simply do not know of any natural process that can be that efficient, that fast, and that focused. Could there be another source entirely? Some theorists point to a different, even more exotic possibility for the briefest bursts. What if the merger does not immediately form a black hole? What if, for a few precious 100 milliseconds, the combined object survives as something called a hypermassive neutron star? This would be a star so massive and dense it should collapse instantly, yet it is temporarily propped up by its insane rate of spin. This object would have a magnetic field trillions of times stronger than Earth's, making it a magnetar on steroids. The decay of that magnetic field, as the star finally gives way and collapses, could inject a final, enormous surge of energy into the jets. This magnetar model might explain bursts with particular patterns of light, offering a different power source rooted in magnetic annihilation rather than gravitational spin. The truth is, we are likely seeing a combination of both. The energy budget of a short gamma-ray burst is a ledger of cosmic extremes, where the columns for spin, magnetism, and gravity are all filled with numbers that defy belief. We can identify the potential accounts, but the actual transaction, the moment the energy is withdrawn and fired into the cosmos, remains hidden behind the event horizon of our knowledge. And if the engine's efficiency is a mystery, the beams it produces are a marvel of cosmic engineering in their own right. The jets must be impossibly narrow to focus all that energy. This is the seventh mystery, the jet structure secret, and it determines whether we are seeing the full fury of the event or just a glancing blow. If the energy of a neutron star merger were sprayed in all directions like a bomb, it would still be powerful, but not universe outshining powerful. To reach the insane luminosities we observe, that energy has to be concentrated into twin beams like cosmic lighthouse beams. But what is the true shape of these beams? Are they simple, uniform cones of light, or are they structured with an intensely bright central core surrounded by a much dimmer, wider sheath? The answer changes everything we think we know. A structured jet means that if Earth lies dead center in the beam's core, we see the full, dazzling power of a classic short gamma-ray burst. But if our view is just slightly off to the side, we see only the fainter edges of the jet. We would record a much weaker burst or perhaps miss it entirely, seeing only the afterglow. This structure explains one of the most perplexing observations. Some short bursts have incredibly faint gamma-ray signals, but their afterglows are surprisingly bright and long-lived. This mismatch is a telltale sign of an off-axis view. We are not looking down the barrel of the jet, but catching it from the side, seeing the wider, less energetic material that was swept up as the jet plowed through space. It is like seeing a flashlight from the side instead of staring directly into the bulb. The structure also suggests why short gamma-ray burst jets seem to be narrower than those from long bursts. The merger environment is cleaner, with less surrounding gas to slow and spread out the jet. It can remain a tight, focused sphere for a longer time. This narrowness has a profound implication. It means we are missing the vast majority of these events. For every short burst that happens to have its jet pointed directly at us, there are hundreds, perhaps thousands, pointed in other directions, their main flash invisible from Earth. Our census of the cosmos's most violent collisions is therefore just a tiny sample, a few lucky alignments in a sea of unseen cataclysms. It forces us to recalculate the true rate of these mergers in the universe, and by extension, how much gold and heavy elements they are actually producing. The jet structure is not just a detail of geometry, it is the key to understanding our own blind spots in the universe. And if our view can be skewed by an angle, what happens when the very fabric of reality is twisted by the explosion itself? The silence that follows a burst can be as revealing as the light itself. This is the eighth mystery, the radio silence puzzle. After the initial gamma-ray flash and the fading X-ray afterglow, astronomers turn their most powerful radio telescopes toward the source. Sometimes they hear a clear, bright signal, a radio echo that can persist for months or even years. But in many other cases, they hear nothing at all, just the empty static of the cosmos. This stark difference is not random noise. It is a direct message about the environment where the neutron stars spent their final moments. Radio afterglow is created by the jet's long-term interaction with its surroundings. As that narrow beam of ultra-fast particles slams into the space outside the merger, it creates a shock wave that plows through any existing gas and dust. This shock wave accelerates electrons to near light speed, causing them to spiral around magnetic fields and emit radio waves. It is the long-lasting echo of the jet's passage, like the sonic boom of a supersonic jet long after the jet itself has vanished. A bright, persistent radio signal tells us the jet ran into something substantial. It means the merger happened within a cloud of interstellar material, a relatively dense neighborhood. This could be the remnant of the star's own stellar winds, cast off during their lives millions of years earlier, or it could be the general gas that fills the star-forming regions of a galaxy. The jet is essentially plowing a path through this fog, and the resulting radio glow tells us the fog is there, but the silent bursts are perhaps even more intriguing. A complete absence of radio emission suggests the jet encountered almost nothing. It raced out into a near-perfect vacuum. This points to a merger in an exceptionally clean environment, like the vast, empty space between stars in an old galaxy, or even in the intergalactic void far from any source of gas. This radio silence is a clue to the life story of the binary system. If the neutron stars were kicked out of their host galaxy long ago, they would have spent billions of years wandering through intergalactic space, a region so empty it contains perhaps 1 atom per cubic meter. By the time they merge, there is simply nothing around for their jet to crash into, resulting in a radio dark event. The presence or absence of this radio whisper therefore acts as a forensic tool. It helps astronomers distinguish between a merger that happened recently within its galactic birthplace and one that was a long-term exile, a final act performed in profound isolation. It adds another layer to the story told by the optical afterglow, helping to map the otherwise invisible landscape around these catastrophic events. And if the environment can vary so dramatically, what does that mean for the very first signal we receive, the one written in gravity itself? The silent radio afterglow points to an environment, but the very first signal from a merger arrives not as light, but as a ripple in space-time itself. The detection of gravitational waves from a neutron star collision in August 2017, an event called GW170817, was a triumph of modern science. For the first time, we felt the universe shake as 2 dead stars spiraled together and merged. And right on schedule, just 1.7 seconds later, the Fermi and Integral satellites saw a short gamma ray burst from the same patch of sky. This was the holy grail of multi-messenger astronomy, the same cosmic event seen through both gravity and light. Yet the celebration was tinged with immediate confusion. The gravitational wave signal was strong and clear, but the gamma-ray burst, named GRB170817A, was shockingly faint. It was about 1,000 times weaker than a typical short burst. If this was the standard merger we had been theorizing about, why was its most famous signature so dim? This mismatch is the 9th mystery, and it forced astronomers to rethink the final moments of a collision in real time. One compelling explanation brings us back to the jet structure. We were not looking down the barrel of the beam. The Earth was positioned slightly off-axis, viewing the jet from an angle. In this scenario, the intensely bright core of the jet missed us entirely. What our satellites detected was the fainter, wider sheath of material surrounding that core, a glancing blow rather than a direct hit. This off-axis view perfectly explains the weakness of the initial gamma-ray flash, but it also predicts something else. As the jet plows into the surrounding space and slows down, its emission becomes less focused and begins to spread out. Days and weeks later, the afterglow from such an event should brighten significantly as the wider structure of the jet comes into our line of sight. Remarkably, that is exactly what happened with GRB170817A. Its X-ray and radio afterglow grew brighter for weeks after the merger, a telltale signature of an off-axis jet finally swinging into view. There is, however, a more dramatic possibility. Some theorists suggest the jet in this event might have been choked. Imagine the newborn jet trying to punch its way out of the dense cloud of debris from the merger. If that cloud is too thick, the jet might struggle to escape, becoming trapped and dissipating its energy internally before it can break free into open space. The result would be a stifled, much weaker burst of gamma rays, or perhaps no burst at all. The fact that we saw any gamma rays suggests the jet in GW170817 did eventually break out, but it may have been a close call, a cosmic struggle between creation and confinement. This landmark event, therefore, did not just confirm a theory, it unveiled a new layer of complexity. It proved that not every neutron star merger produces a classic, brilliant short gamma ray burst. Some are faint, some are off-axis, and some might be completely dark in gamma rays, their jets entirely smothered. This raises a profound and unsettling question. Our gravitational wave detectors are now listening to the universe's tremors regularly. Many of the collisions they hear are between black holes which produce no light. But some are likely neutron star mergers. How many of those have we missed because their gamma ray beam was pointing away from us or because it was choked at birth? For every brilliant short burst we see, there could be a silent majority, invisible cataclysms whose only announcement is a subtle shiver in the fabric of spacetime. The universe may be far more violent and far more secretive than its light alone has ever revealed. Our gravitational wave detectors are listening for those silent cataclysms, and their data is revealing a startling contradiction. This is the 10th mystery, the rate discrepancy. Based on our understanding of how stars live and die, astronomers can calculate a theoretical number. In a galaxy like our Milky Way, a pair of neutron stars should spiral together and merge roughly once every 10,000 to 100,000 years. That sounds rare, but across the observable universe with its hundreds of billions of galaxies, it means thousands of these events should be happening every single day. Yet the number of short gamma ray bursts we actually detect is far, far lower. Our space telescopes like Fermi and Swift might catch only a few dozen each year. So where are all the missing mergers? This glaring mismatch is a crisis for our models, and it points to several unsettling possibilities. The first, and perhaps most profound, is that the majority of neutron star mergers are completely dark in gamma rays. We already saw how an off-axis jet or a choked jet could make a merger invisible to our gamma-ray satellites. If most jets are narrow, or if they often fail to break free from the debris, then the brilliant flashes we chase might be the rare exceptions, not the rule. For every short burst we see, there could be 100 silent mergers. Their only signal a faint ripple in spacetime that only gravitational wave observatories can hear. This idea is being tested right now. Every time the LIGO and Virgo detectors sense a gravitational wave from a neutron star collision, astronomers across the globe scramble to look at that patch of sky. More often than not, they find no accompanying flash of gamma rays. Those are the dark mergers, and each one suggests our gamma ray view of the universe is fundamentally incomplete. The second possibility is that our estimates of the merger rate within galaxies are simply wrong. Perhaps binary neutron star systems are rarer than we think. Maybe the supernova kicks that create them are so violent they often destroy the binary, sending the stars flying apart alone instead of keeping them bound together. Or perhaps the time it takes for their orbits to decay and merge is much longer than our models predict, meaning the universe hasn't had enough time since the first stars died to produce the flood of mergers we expect. This rate discrepancy isn't just an academic tally, it has cosmic consequences. If mergers are rarer, then the amount of heavy elements like gold and platinum they produce must be recalculated. Could these collisions really be the primary source of all the gold in the universe if they happen so infrequently? Or are there other, even more exotic factories we haven't yet discovered? Conversely, if mergers are common but mostly dark, then the universe might be seeded with far more precious metals than we ever imagined, silently enriching galaxies with every unseen collision. The answer lies in the growing synergy between light and gravity. As gravitational wave detectors become more sensitive, they will hear more of these quiet mergers. By comparing the number they detect with the number we see in gamma rays, we will finally measure the true fraction that are dark. This will solve the rate mystery, but in doing so, it will force us to rewrite the cosmic ledger for some of the most valuable elements in existence. The faintest bursts might point to a different kind of monster entirely. If the energy of a merger does not immediately vanish into a black hole, what survives? The 11th mystery asks a startling question. Could some short gamma-ray bursts be powered not by a black hole spin, but by the birth of an impossibly magnetized star? This is the magnetar alternative. In this scenario, the two merging neutron stars are not quite heavy enough to trigger instant collapse. For a precious few hundred milliseconds or even longer, the combined object holds out against gravity. It forms a hypermassive neutron star, a temporary remnant spinning so fast it is nearly flying apart, and crucially, it possesses a magnetic field of almost inconceivable strength, making it a newborn magnetar. The energy stored in that magnetic field is apocalyptic. As the star's furious spin gradually slows, its magnetic field lines twist, snap, and reconnect in a storm of violence. This process can dump enormous energy into the surrounding debris, potentially powering a gamma-ray burst and shaping its long-term afterglow in unique ways. The key to solving this mystery lies not in the initial flash, but in what comes after. A magnetar central engine leaves a specific fingerprint, a lingering energy source. Astronomers search for it in the X-ray afterglow. In many short bursts, the X-ray light fades predictably like a cooling ember, but in a significant fraction, something strange happens. The fading suddenly halts, the X-ray brightness plateaus, remaining steady for hours, sometimes even days, before finally resuming its decline. This is not what you expect from a simple fireball coasting through empty space. A plateau suggests a central engine that is still active, still pumping energy into the aftermath long after the merger is over. A newborn black hole with its energy tied to a fast-vanishing accretion disk cannot easily explain this. A magnetar, however, can. The spinning magnetar acts like a battery, its rotational energy being steadily converted into X-rays and particle winds that continuously re-energize the afterglow, creating that sustained plateau. It is the cosmic equivalent of a light that won't turn off because someone is still holding down the switch. Yet, the evidence is not clear-cut. Distinguishing between a magnetar and a black hole engine is incredibly difficult from billions of light years away. The plateau could also be produced by a black hole if it is fed by a particularly long-lived disk of debris, or if the jet is interacting with an unusually dense environment. The smoking gun would be the detection of periodic signals, like faint X-ray pulsations from the spinning magnetar, but those signals would be buried in incredibly noisy data, and the magnetar's life may be tragically short. If it is too massive, it will collapse into a black hole within minutes or hours, cutting off its own signal. So we are left with tantalizing clues, not convictions. Some short bursts fit the magnetar model beautifully, their afterglow light curves looking exactly like theoretical predictions. Others show no such signs, perfectly matching the black hole scenario. This suggests the universe is not picky. Some mergers create a bottomless pit in spacetime. Others create a magnetic monster that rages against the dying of the light, if only for a little while. The true mystery is determining which is which, and in doing so, understanding the ultimate fate of matter pushed beyond the brink of collapse. The universe's classification system is not as clean as we would like. This leads us to the 12th mystery, the short, long-burst imposters. Events that live in a twilight zone of duration and defy our neat categories. For decades, gamma-ray bursts were sorted into two simple bins. Short bursts lasted less than 2 seconds, and long bursts lasted more than 2 seconds. It was a clean, observational rule of thumb that pointed to two different cosmic origins. But the cosmos loves exceptions. A small but significant number of bursts hover right around that 2-second boundary. They are neither definitively short nor clearly long. They are the hybrids, the cosmic chimeras that force us to ask, what exactly are we looking at? The duration of a burst is a direct clue to its central engine's life. A long burst from a collapsing massive star has a sustained fuel supply leading to a longer event. A short burst from a merger has its fuel exhausted almost immediately. So a burst that lasts exactly 2 seconds is an engine that cannot decide how long to run. One compelling suspect for these imposters is a different kind of catastrophic marriage, a neutron star merging not with another neutron star but with a black hole. In this scenario, the black hole is the more massive partner, and the dance is even more one-sided. The neutron star is slowly torn apart by the black hole's gravity before being swallowed. The process of tidal disruption, the stretching and shredding of the star, could provide a slightly longer stream of material to feed the black hole's jets than a quick neutron star collision. This might produce a burst that is longer than a typical short burst, but still shorter than a true long burst from a stellar collapse. It is a Goldilocks event, not too brief, not too prolonged. Another possibility is that we are seeing a short burst from a neutron star merger, but viewed from a very specific oblique angle. If we are looking through the outer layers of a structured jet, the signal might be stretched out in time, appearing longer than it truly is at its core. Or perhaps some neutron star mergers leave behind a magnetar that takes a few extra seconds to collapse, its magnetic fury extending the burst duration. The existence of these hybrid events is a stark reminder that nature does not care for our human-made boundaries. The 2-second divide is a useful guideline, not a law of physics. The true nature of a burst is written not just in its duration, but in the entire symphony of its emission, its afterglow, and the environment it reveals. Each imposter event is a case study, a puzzle that forces astronomers to look beyond the stopwatch and examine the finer details of the light curve, the spectrum, and the host galaxy. By solving the mystery of these boundary crosses, we may discover entirely new pathways for stellar death, proving that the final moments of massive objects can play out in more ways than our textbooks have yet described. The hybrid bursts prove that nature refuses to be neatly categorized, and that uncertainty extends to one of their most promising roles in cosmology. Short gamma-ray bursts have been proposed as potential lighthouses for measuring the vastness of the universe itself. They are so brilliant they can be seen from the farthest cosmic shores, offering a way to gauge distances to galaxies billions of light-years away. The idea is to use them as standardizable candles, much like the famous Type 1, a supernova. If we can find a relationship between how a burst looks and how intrinsically bright it is, we can calculate its true distance. That calculation is the first rung on the cosmic distance ladder, a tool to measure how fast the universe is expanding. But here lies the 13th mystery. How can we trust these explosions as cosmic rulers when every one of them seems to be an individual? The fundamental problem is that short gamma-ray bursts are not stamped out by a cosmic factory. They are not identical. The energy of the central engine can vary from merger to merger. A collision that forms a more massive black hole with a faster spin might produce a more powerful jet than a merger that leaves behind a magnetar. Even more critically, our viewing angle introduces a massive uncertainty. As we learned, seeing a jet head-on versus from the side can change the observed brightness by a factor of 1,000 or more. If we mistake a faint, off-axis burst for a truly low-energy one, our distance calculation will be catastrophically wrong. Astronomers are working to solve this by looking for correlations. They search for relationships between the burst's duration, its spectrum, the brightness of its afterglow, and how quickly that afterglow fades. The hope is to find a signature in the light curve, a kind of fingerprint that reveals the burst's true power regardless of our viewing angle. For instance, the timing of a peak in the afterglow's brightness might tell us the jet's opening angle, letting us correct for the geometry. It is a painstaking process of calibration, using the few bursts where we have independent distance measurements, perhaps from their host galaxies, to test and refine these models. Why go through all this trouble? Because if we can standardize them, short gamma-ray bursts become a revolutionary probe. They can reach back to an era before Type 1, a supernova, were common, to a younger, more turbulent universe. By measuring distances at these extreme ranges, we can trace the history of cosmic expansion with unprecedented precision. This is the key to understanding dark energy, the mysterious force accelerating that expansion. Does dark energy's strength change over time, or has it been constant? The answer is written in the geometry of space-time, and the most brilliant flashes in the universe might be the only beacons bright enough to illuminate it. But to read that message, we must first solve the riddle of their inconsistency, learning to see past their dazzling differences to the fundamental physics that unites them all. The search for a cosmic ruler is complicated by where these rulers are built. The galaxies that host short gamma-ray bursts are not all the same, and their differences tell a story of immense patience. Some bursts are found in massive, red, elliptical galaxies, places where star formation ceased billions of years ago. These are quiet retirement communities for ancient stars. Other bursts appear in blue, spiral galaxies like our own, where new stars are still being born in bright, gassy arms. This split personality is the 14th mystery. If all neutron stars are born from the explosive deaths of massive, short-lived stars, why do we find their mergers in such wildly different galactic neighborhoods? The answer is written in a concept called delay time. It is the silent gap between the birth of the binary system and its final, cataclysmic merger. This delay can be staggeringly long. Imagine two massive stars are born together in a bustling, star-forming spiral galaxy. They live fast, die young, and leave behind a pair of neutron stars in a tight orbit. But their orbit is not yet tight enough to merge. They must lose energy, slowly spiraling inward over eons. This process can take billions of years. By the time they are finally ready to collide, their entire galaxy may have transformed. That once vibrant spiral, through collisions and the quiet aging of its stars, may have settled into a smooth, red elliptical galaxy. The burst then appears in this old galaxy, but its progenitors were actually born in a much younger universe. The host galaxy, in this case, is not a birthplace, but a retirement home where the binary system finally completed its long decay. Conversely, a short burst in a star-forming spiral galaxy suggests a much shorter delay time. Perhaps the neutron stars were born with orbits already so tight that gravitational wave emission brings them together in only a few 100 million years. Their merger happens while their host galaxy is still young and actively making stars, a quick tragedy following swiftly after the stellar deaths that created them. This duality forces astronomers to become cosmic historians. By carefully classifying the host galaxy, its color, its mass, its star formation rate, they can estimate the likely age of the progenitor system. A burst in an elliptical galaxy points to a patient, ancient binary that wandered the cosmos for most of the universe's history before its final moment. A burst in a spiral suggests a more impulsive pair rushing to their doom. This also helps explain the lone wolf bursts in seemingly empty space. A binary with a strong supernova kick at birth could be ejected from its galaxy entirely, spending its entire multi-billion-year delay time as an intergalactic wanderer before merging in the void. The host galaxy, or lack thereof, is therefore a fossil record. It holds the memory of the binary's entire life story, from its violent birth in a stellar nursery to its long, silent journey through a changing cosmos. But if that journey can span the age of the universe, what does it mean for the very first mergers, the ones that lit up the cosmic dawn? The host galaxy tells the story of their long journey, but the radioactive glow that follows their collision reveals the chemistry of their destruction. This is the 15th mystery, the kilonova diversity. When two neutron stars merge, the material blasted out is not just debris, it is a radioactive forge, producing heavy elements that decay and emit light. Astronomers call this glow a kilonova, and it is the signature of cosmic alchemy in action. Yet these kilonovae are not uniform. Some shine with a brilliant, hot blue light in their first hours. Others appear red and cooler from the very beginning. This variation in color is a direct message about what was created in the blast, and it points to a far more complex process than we first imagined. The color tells us about the composition and the speed of the ejected material. A blue kilonova suggests lighter heavy elements like strontium and silver, and a faster-moving, less dense ejector. A red kilonova points toward heavier elements like gold, platinum, and lanthanides, which form in slower, denser outflows that better obscure the inner, hotter light. So what determines which recipe a merger follows? The answer lies in the precise physical parameters of the catastrophic event. The masses of the two neutron stars are crucial. A merger of two relatively light neutron stars might eject more material overall, but in a less neutron-rich state, favoring lighter R-process elements and a bluer glow. A merger involving a very massive neutron star could produce a denser, more neutron-rich environment, cooking up the heaviest atoms and resulting in a redder kilonova. The presence of a remnant magnetar, even for a short time, could also dramatically change the outcome. Its intense magnetic winds might heat the ejector, keeping it blue for longer, or it might blow away the lighter material first, leaving behind a shell rich in the heaviest elements that appears red. Even the asymmetry of the collision matters. If the merger is lopsided, it can launch material in specific directions at different speeds, creating a patchy, multi-colored kilonova that changes depending on our viewing angle. Each kilonova is therefore a unique fingerprint of the explosion. By carefully dissecting its light curve and spectrum, astronomers can work backwards, attempting to reconstruct the masses of the progenitors, the nature of the remnant, and the exact conditions in that nuclear cauldron. This turns every detected kilonova into a cosmic laboratory, one where we can observe the formation of elements we cannot create on Earth. The diversity we see means the universe has many recipes for destruction, each yielding a slightly different periodic table of byproducts. It suggests that the gold in one galaxy might have a slightly different origin story than the gold in another, forged in mergers with subtly different dances of mass and magnetism. The kilonova's unique fingerprint reveals the chemistry of a single event, but to understand the full story we must find the systems before they explode. This is the 16th mystery, the search for the missing progenitors. We have overwhelming indirect evidence that binary neutron stars exist and merge. We have seen the afterglows, we have heard the gravitational waves, and we have witnessed the kilonovae. Yet, in our own cosmic backyard, the Milky Way, directly spotting a pair of neutron stars that are definitively on a collision course is like finding a ticking time bomb with a fuse set for millions of years. Where are they? The most successful hunt uses the cosmic lighthouses we call pulsars. When a neutron star spins and beams radio waves toward Earth, we detect it as a pulsar, a celestial metronome of incredible precision. Radio astronomers, through immense surveys that scan the sky night after night, listen for the subtle heartbeat of these objects. Finding a pulsar in a binary system is a major discovery. Finding one orbiting another neutron star is the ultimate prize. To date, we have only confirmed a handful of these double neutron star binaries in our entire galaxy. The most famous is the Hulse-Taylor binary, discovered in 1974. Its two neutron stars are spiraling inward exactly as Einstein's theory predicts, and they will merge in about 300 million years. It was the first direct proof that such systems exist and that they emit gravitational waves. But here lies the challenge. The Hulse-Taylor binary will merge, but not for an astronomically long time. We need to find binaries with much shorter fuses, systems that are so close together they will collide on a timescale comparable to the age of the universe, making them potential sources of the short bursts we see. Predicting which binaries have these short merger times is a complex puzzle. It depends on their current separation, their orbital eccentricity, and their masses. A single measurement error can change the predicted merger time by billions of years. It is like trying to predict the exact second a distant, wobbling top will fall over based on a single blurry photograph. Furthermore, many of these systems might be invisible to us. If the pulsar's beam does not point toward Earth, we will never hear its radio pulse. The binary could be there, silent and dark, its deadly dance completely hidden from our view. Or one or both neutron stars might simply be too old and have faded, their magnetic fields too weak to produce detectable pulsar emission. They become cosmic ghosts, known only by their gravitational influence on a visible companion, which is extraordinarily difficult to measure. So the systems we have found are likely just the visible tip of a vast, dark iceberg. Every new double neutron star binary discovered is a data point that helps calibrate our models of population synthesis, which estimate how many such systems should exist and how often they merge. But the gap between the few we see and the many we infer is a constant reminder of our blindness. We are detectives searching for needles in a galactic haystack, knowing that most of the needles are made of a material that does not reflect light. The quiet patience of these systems is itself awe-inspiring. They spend eons in a slow, silent spiral, a countdown set in motion by the deaths of two stars. Finding them is not just about completing a census, it is about identifying the future flashpoints of our galaxy, the places where, millions of years from now, a brief cataclysm will briefly outshine every star in the night sky and seed the cosmos with newly forged gold. The search for their silent companions leads us to one of the most elusive signals of all. Short gamma-ray bursts are not just beacons of light, they are cosmic cannons, blasting out particles at energies that dwarf anything our most powerful human colliders can produce. Within those relativistic jets, protons and atomic nuclei are whipped to velocities infinitesimally close to the speed of light, gaining energies millions of times greater than the particles in the Large Hadron Collider. This makes them prime suspects for the origin of ultra-high-energy cosmic rays, the most energetic particles ever detected striking our atmosphere. But the evidence for this is so far entirely circumstantial. The true smoking gun would be the detection of a different kind of messenger, one that travels unimpeded across the universe, a neutrino. This is the 17th mystery. Despite decades of searching, not a single high-energy neutrino has been definitively linked to a short gamma-ray burst. Their silence is a profound puzzle. The theory is compelling. Inside the jet's chaotic maelstrom, protons can collide with photons or other particles, creating unstable particles called pions that quickly decay. This decay produces both gamma rays and, crucially, neutrinos. A neutrino is a ghostly, nearly massless particle that barely interacts with matter. It can travel in a straight line from the heart of the explosion, passing through dust, gas, and even entire planets without a trace. If we could catch one that arrived at the same time and from the same direction as a short burst, it would be direct proof that protons are being accelerated to extreme energies within the jet. It would confirm these events as cosmic p-vatrons, machines that can pump out particles at peta-electronvolt scales. So why haven't we seen them? The challenge is one of needle and haystack on a universal scale. Detectors like IceCube, a cubic kilometer of instrumented ice at the South Pole, watch for the extremely rare flash of light created when a neutrino does interact with the ice or water. They are buried deep to shield them from other cosmic radiation. Every day they are flooded with signals from atmospheric neutrinos created when cosmic rays hit our own atmosphere. Picking out a single neutrino from a specific short burst, which might be billions of light years away, is like trying to hear a specific whisper in a roaring stadium. The expected flux from a single burst is incredibly faint. Even if the jet is a prolific neutrino factory, by the time those ghostly particles cross the cosmic distances to reach us, they are spread incredibly thin. Our detectors may simply not be sensitive enough to catch more than a handful from the very nearest, most powerful events. There is also a timing problem. The neutrino signal is predicted to be nearly simultaneous with the gamma-ray flash, arriving within seconds. This requires perfect coordination. The gamma-ray satellites must instantly alert the neutrino observatories, which must then scour their data for a candidate that matches the precise coordinates and time. A delay of minutes can mean the data is already overwritten or too buried in noise to recover. Yet the potential reward makes the hunt irresistible. A successful link would be a transformative moment. It would open a new window into the jet's hidden engine. By analyzing the neutrino's energy, we could learn about the density of protons in the jet, the magnetic field strengths, and the exact mechanisms of particle acceleration operating in conditions we can never recreate. It would tell us what fraction of the burst's colossal energy is going into accelerating particles versus producing light. More than that, it would solve a century-old mystery in astrophysics, finally pinpointing one of the dominant sources of the universe's most energetic particles. Every time a short burst flashes in the sky, enormous, silent telescopes buried in ice and under the sea are listening intently for the faintest echo of a ghost, hoping for a whisper that will reveal the violent heart of the collision. The hunt for spectral lines in short gamma-ray bursts is a search for cosmic ghosts. For decades, astronomers have pointed their most sophisticated telescopes at these brilliant flashes, hoping to catch a telltale fingerprint in the light. When you pass light through a prism, it breaks into a rainbow of colors, a spectrum. Embedded in that spectrum are dark or bright lines, each one a barcode for a specific element. Iron, calcium, oxygen, each atom imprints its own unique signature. Finding these lines in a burst's afterglow would be a direct chemical analysis of the explosion site, revealing what the environment is made of and in what quantities. For long gamma-ray bursts this works. Their slower, brighter afterglows often show the clear signatures of iron and other heavy elements, proving they exploded within dense clouds of stellar material. But for short bursts, the result is a profound and consistent silence. No conclusive atomic signatures have ever been found. The light arrives, brilliant and featureless, a smooth continuum that offers no chemical clues. This spectral void is the 18th mystery. Why does the light from the universe's most violent stellar collisions reveal nothing about what they are made of? The answer likely lies in the very nature of the event. To produce a spectral line, atoms must be relatively cool and undisturbed, able to absorb or emit light at their specific, quiet frequencies. The environment of a short gamma-ray burst is the exact opposite of cool and quiet. First, consider the intense radiation. The initial flash of gamma rays is so powerful it can completely ionize any matter for light years around, stripping electrons from atoms with brute force. An atom missing its electrons is just a naked nucleus. It cannot produce the delicate spectral lines astronomers seek. The surrounding material is blasted into a plasma, a superheated soup of charged particles that emits a smooth, featureless glow. Second, there is the issue of density. Spectral lines also require a sufficient number of atoms to make a detectable signal. The leading models suggest neutron star mergers happen in exceptionally clean environments, as the radio silence hinted. If there is very little surrounding gas, just a few stray atoms per cubic centimeter, then even if those atoms survived the radiation blast, there simply aren't enough of them to paint a visible line in the spectrum. It is like trying to detect the color of a single drop of ink lost in an ocean. The merger site is a sterile operating room, scrubbed clean by eons of stellar winds or exile in intergalactic space, leaving nothing behind to leave a chemical signature. There is a more exotic possibility. The material that is present might be moving at such relativistic speeds, a significant fraction of light speed, that any spectral lines are Doppler shifted beyond recognition. The lines are smeared across a huge range of frequencies, blending into the background continuum until they become invisible. Or perhaps the dominant elements forged in the kilonovae, like gold and platinum, have spectral lines that are inherently faint and in awkward parts of the electromagnetic spectrum, making them devilishly hard to pick out from billions of light years away. This spectral silence is itself a powerful clue. It reinforces the picture of a short burst as a precise surgical event. It does not occur in a murky stellar nursery, but in a near-perfect vacuum where its energy meets almost no resistance. The absence of lines tells us about the emptiness that surrounds the cataclysm, an emptiness that allows the jet to remain focused and powerful. So while astronomers may never get a neat chemical barcode from the heart of the merger, the blank spectrum speaks volumes about the stark, unforgiving stage upon which this cosmic drama plays out. The blank spectrum reveals a clean stage, but on rare occasions, a different kind of light erupts in the darkness. A fleeting, brilliant flash of visible light arrives in perfect lockstep with the gamma rays themselves. For most short bursts, the optical sky remains dark until the afterglow emerges minutes later. But for a tiny, precious few, the universe flips on a white-hot strobe for a fraction of a second. This is the prompt optical flash, and its extreme rarity makes it the 19th mystery. What could possibly produce visible light so quickly from an event whose primary signature is the highest energy radiation we know? The timing is the critical clue. This flash is not the later afterglow. It is simultaneous with the gamma-ray pulse, meaning it must be generated by the same catastrophic engine, or at the very least by processes occurring in the same instant. One possibility takes us deep inside the jet's formation. As the relativistic jet punches its way out of the merger debris, it creates a shock wave not in the external medium but within itself. Internal collisions between faster and slower shells of material inside the jet could produce this brief, multi-wavelength flash, including optical light. It would be like seeing the sparks fly from a grinding wheel at the exact moment it touches metal. Another, more exotic theory places the origin even closer to the heart of the violence. It suggests the flash comes from the radioactive fireball of the kilonova itself, ignited astonishingly fast. In this scenario, the neutron-rich material ejected during the merger is so hot and dense from radioactive decay that it begins glowing in visible light almost immediately, its birth cry arriving at the same time as the gamma rays from the jet. This would mean we are seeing two separate components of the same explosion, the narrowly focused jet pointed at us and the spherical, expanding glow of freshly forged elements. Distinguishing between these origins is a monumental observational challenge. Capturing the prompt optical flash requires incredible luck and robotic speed. A telescope must already be pointing at that exact patch of sky at the exact millisecond the burst occurs, or a satellite must trigger an alert so fast that ground-based telescopes can swing into position within a second. Most of the time, by the time any instrument looks, the flash is already gone, vanished into history. Its rarity suggests that the conditions to produce it are special. Perhaps it requires a specific viewing angle or a particular balance of energies between the jet and the ejected material. Maybe only mergers that produce a certain type of magnetar remnant can power such a brilliant, instant optical signal. Each detected flash is therefore a treasure, a direct snapshot of the explosion's first heartbeat. By analyzing its color and its exact timing relative to the gamma rays, astronomers hope to decode the sequence of events in those first chaotic moments. Does the optical light rise and fall with the gamma rays, or does it have its own independent pulse? The answers could map the geometry of the explosion in a way no other signal can. This elusive flash is more than just another wavelength of light. It is a strobe illuminating the very instant of creation, freezing a frame of the cosmic engine at its moment of maximum fury. If we can learn to read its brief message, we might finally see the structure of the cataclysm not as a theoretical model, but as a reality painted in sudden, brilliant white light. The sudden brilliance of a prompt optical flash offers a fleeting glimpse into the engine's birth, but the gamma rays themselves might carry an even deeper imprint from the edge of reality. The highest energy photons from a short burst have traveled for billions of years across the cosmos. According to Einstein's general relativity, all light, regardless of its energy, should travel at the same perfect speed in a vacuum. But some theories of quantum gravity suggest that on the tiniest imaginable scales, space-time itself might not be smooth. It could be foamy, a seething quantum froth where the very concepts of distance and time break down. Crossing this microscopic foam, a journey of billions of light years, could leave a subtle mark on the light. The highest energy photons might be slowed down ever so slightly, or their polarization could be scrambled. It is as if the pristine signal from the burst passes through a cosmic filter of unimaginable fineness. Detecting such an effect would be a direct test of physics beyond Einstein, a potential window into the quantum nature of space-time itself. This is the time reversal test, the 20th mystery. The name comes from a peculiar idea. If the highest energy photons are delayed, they would arrive later than their lower energy counterparts. When astronomers analyze the light curve, this could make the burst appear to unfold in reverse order, with high-energy emission seeming to peak after low-energy emission. It is a bizarre fingerprint of physics at the Planck scale, written in the light of the universe's most powerful explosions. The hunt for this signature is a monumental task of data archaeology. Scientists meticulously dissect the gamma-ray signal from powerful bursts, looking for any systematic delay or polarization change correlated with photon energy. They need bursts from the farthest possible distances because the effect, if it exists, would accumulate over the immense journey. A short gamma-ray burst from the edge of the observable universe is the ideal laboratory. Its light has passed through more quantum foam, in theory, than any light from within our galaxy. Yet, the expected signal is vanishingly small, likely buried in the natural statistical noise of the explosion itself. Distinguishing a quantum gravity delay from other astrophysical effects within the jet is like trying to hear a single wrong note in a symphony played during a hurricane. So far, no convincing evidence has been found. The light from short bursts continues to obey Einstein's classic rules with frustrating perfection, but the search continues with every new detection. Each powerful, distant burst is another chance to see if the fabric of spacetime leaves a trace on the light that tears through it. The silence so far is not a defeat but a measurement. It places ever tighter constraints on the possible theories of quantum gravity, ruling out models that predict effects too large to have been missed. The universe's most brilliant flashes are thus proving to be the ultimate physics laboratories, testing the laws of existence on scales both vast and infinitesimal. That same light, stretched thin by its cosmic journey, carries the chemical signature of everything it has passed through. The vast voids between galaxies are not completely empty. They are filled with the intergalactic medium, a diffuse fog of hydrogen and helium gas so thin it makes the best laboratory vacuum on Earth seem dense. This gas is nearly impossible to see directly, but it leaves its mark on light traveling through it. When the afterglow of a short gamma-ray burst shines from billions of light years away, its light acts like a probe beam. As it passes through this cosmic fog, atoms in the medium absorb specific wavelengths, creating dark lines in the afterglow's spectrum. It is as if the burst hands us a flashlight, and by seeing which colors are dimmed on its long journey to Earth, we can map the composition and structure of the invisible cosmic web. This turns every distant burst into a chance to perform a chemical biopsy on the universe's emptiest regions, yet the results are not always what we expect. The absorption features, the chemical fingerprints imprinted on the light, sometimes tell a strange story. The expected signatures of pristine hydrogen and helium are there, but occasionally, astronomers detect the faint traces of heavier elements like carbon, oxygen, and silicon. This is the 21st mystery, a clue written in missing light. How did these heavier atoms, which are forged only in the hearts of stars and scattered by supernova, end up floating in the profound emptiness between galaxies? Their presence suggests the intergalactic medium is not a pristine relic from the Big Bang. It has been polluted, enriched by generations of stars that lived and died, even in the loneliest reaches of space. One possibility is that the short burst itself is the culprit, perhaps the galaxy that hosted the progenitor binary long before the merger had a violent past. Galactic winds from countless supernova could have blown these heavy elements out into the intergalactic void, seeding the emptiness with stellar ash. The binary neutron star system then formed within this already enriched halo, and when it was finally ejected or when it merged, its light passed through this previously polluted region. We are not seeing the general intergalactic medium, but a local bubble of chemically enriched gas, a fossil of that galaxy's ancient outbursts. Another, more tantalizing idea points to the cosmic web itself. This vast structure, made of dark matter and gas, filaments and nodes, is where galaxies form and evolve. The heaviest elements might be transported along these invisible filaments, carried by vast flows of gas that feed growing galaxies. A short burst line of sight might pierce one of these dense filaments, revealing a strand of the cosmic web that is far richer in heavy elements than our models predict. The differences in absorption could then be a map of the web's uneven chemical enrichment, showing us where the universe has been busy building and recycling matter on the largest scales. Or the explanation could be more local and dramatic. What if the absorption comes not from a static fog, but from the expanding shell of the kilonova itself? The cloud of newly forged heavy elements blasted out from the merger could be expanding at a significant fraction of light speed. If this cloud lies along our line of sight to the afterglow, it would imprint its own fresh spectral signatures, the fingerprints of gold and platinum being created in real time onto the light. Distinguishing this signal from the ancient intergalactic medium is a spectral detective story of immense complexity. Each anomalous absorption line is therefore a historical record. It tells of galactic winds that howled across millions of light years, of filamentary rivers of enriched gas in the cosmic dark, or of the immediate aftermath of the collision we are witnessing. By solving why these features differ, we are not just studying the burst, we are using its brilliant flash to illuminate the hidden architecture and the chemical history of the cosmos, reading the universe's diary in the shadows cast by its most fleeting beacons. The chemical history written in their light begins with the birth of the stars themselves. Before two neutron stars can spiral together in a cataclysm, they must first exist as a pair. This is the 22nd mystery, the binary formation path, and it asks how the universe forges these deadly partnerships in the first place. The life story of the progenitors is not just background lore, it dictates everything about the eventual merger, from where it happens to how often it occurs. There are two leading and competing cosmic narratives for their creation, and the evidence points to both being possible. The first is a story of quiet, isolated evolution. Imagine two massive stars born together in a stellar nursery, bound by gravity from their very first breath. They orbit each other while they burn through their nuclear fuel over millions of years. The more massive star explodes first as a supernova, leaving behind a neutron star. Miraculously, the explosion does not blow the binary apart. the system survives, though it may receive a kick that sends it careening through its galaxy. The second star then lives out its life, eventually swelling into a giant. During this phase, matter can spill over onto the neutron star companion, spinning it up and possibly recycling it into a millisecond pulsar. Finally, the second star too goes supernova. If the binary survives this second violent explosion, the result is a pair of neutron stars, now locked in a slow gravitational death spiral. This isolated binary path predicts mergers that occur relatively close to where the stars were born, often within the galactic disk. It also suggests the spins of the two neutron stars could be aligned with each other and with their orbit, a legacy of their shared, orderly evolution. The second story is one of chaos and dynamic encounters. It begins not with a quiet binary, but in a dense stellar environment like a globular cluster, a spherical swarm of millions of ancient stars. Here, single neutron stars created from lone massive stars long ago wander through the crowded cluster. Close gravitational encounters are common. Sometimes, two lone neutron stars can be thrown together by a passing star, forming a binary through this dynamic capture. More often, a neutron star might capture a normal star and through a complex series of exchanges and interactions, eventually trade up for another neutron star. This dynamical formation path is violent and random. It predicts that the spins of the two neutron stars will have no relationship to each other or their orbit. They will be pointed in completely random directions, a testament to their chaotic origins. These mergers would happen right inside the globular cluster, far from the star-forming regions of a galactic disk, and could be ejected into intergalactic space. Each path leaves a different imprint on the population of mergers we see. The isolated binary model might produce a steady, widespread drizzle of events across spiral galaxies. The dynamical model would create bursts of activity in specific, dense clusters, and could potentially produce mergers much faster, as captured binaries often start with very tight orbits. The spin orientations are a potential smoking gun. When we finally detect gravitational waves from many more mergers, subtle details in the signal could reveal if the stars were spinning in alignment or tumbling chaotically. That single piece of information would tell us which story was true for that particular pair. The reality is that our universe likely employs both methods, building some neutron star pairs through quiet cosmic marriage and others through violent stellar bar fights. This duality explains the diversity we see in host galaxies and in the bursts themselves. It means that the journey to that final, brilliant second is not one story, but many, a tapestry of cosmic fates woven from both order and chaos. The chaotic origins of these binary systems determine the final weight of the wreckage. When two neutron stars finally collide, the total mass of the remnant is the ultimate arbiter of its fate. But nature has drawn a puzzling line in the sand. On one side, we have neutron stars, the densest stable objects we know, with observed masses up to about 2.2 times that of our Sun. On the other side, we have black holes, the lightest of which seem to start at around 5 solar masses. Between 2.2 and 5, there is a strange desert, a conspicuous absence of objects. This is the mass gap, and it creates the 23rd mystery. What exactly happens when a neutron star merger produces a total mass that lands squarely in this forbidden zone? If two fairly heavy neutron stars, each weighing 1.8 solar masses, slam together, their combined mass is 3.6. This number sits directly in the gap, too heavy to be a stable neutron star, yet seemingly too light to be a classic black hole. So what does it become? The answer hinges on the most extreme physics imaginable. One possibility is an immediate, silent collapse. The merged object is so unstable that it lasts for less than a millisecond before the inward pull of gravity becomes irresistible. It vanishes into a black hole almost instantaneously, offering no time for a sustained central engine. This might produce a very weak gamma-ray burst, or perhaps none at all, just a gravitational wave chirp followed by silence. The other, far more intriguing possibility is the formation of a hypermassive neutron star. This is a temporary monster, a star so massive it should collapse, but it is temporarily held up by two powerful forces. The first is its insane rate of spin. Like a potter's wheel keeping a lump of clay from flying apart, the furious rotation provides an outward centrifugal force that fights gravity. The second is the exotic nature of matter at these densities. We simply do not know the true equation of state of neutron star material. It might be stiff, resisting compression so effectively that it can support a heavier object, if only for a little while. This hypermassive remnant could survive for hundreds of milliseconds or even for several seconds before finally succumbing. That brief window of existence would be a cosmic spectacle. It would allow for a longer-lived, more energetic central engine, potentially powering a brighter gamma-ray burst and a distinctive afterglow. Its powerful magnetic fields could also shape the ejected material in unique ways, influencing the color and evolution of the kilonova. This is where gravitational wave astronomy becomes our most crucial tool. The chirp from a merger doesn't just tell us it happened, it carries an intricate fingerprint of the masses and spins of the objects involved. More importantly, the signal doesn't end at the moment of collision. The post-merger signal, the ring down, holds the key. If the remnant is a hypermassive neutron star, it will oscillate and vibrate like a struck bell before it collapses. These vibrations, tiny wobbles in spacetime itself, would imprint a specific set of frequencies onto the gravitational wave signal. Detecting those frequencies would be a direct confirmation that a temporary star existed in the gap, defying gravity for a glorious, fleeting moment. If, on the other hand, the signal cuts off abruptly with no ring down, it points to a prompt collapse, a swift and total victory for the black hole. Every merger we detect in or near the mass gap is therefore a fundamental experiment. It tests the limits of matter itself, probing the physics of a substance squeezed beyond anything we can replicate. The outcome tells us how stiff or soft neutron star material truly is, and for how long a star can dance on the very edge of oblivion. Solving the mass gap mystery does more than categorize a remnant. It reveals the ultimate strength of the forces that hold our universe together, measured in the final, trembling vibrations of a star that should not exist. The temporary star in the mass gap offers a final, furious spin, but its birth is shrouded by the wreckage of its parents. That debris holds a clue to a quieter, longer history. Long before the final collision, during the billions of years the neutron stars spent spiraling together, their evolution may have left a ghostly trace in the space around them. This is the 24th mystery, the question of the circumbinary disk. Could some merging neutron stars be surrounded by a vast, faint ring of gas and dust, a relic from their earlier lives as stars? The idea is not as far-fetched as it sounds. Before the first neutron star formed, one of the massive progenitor stars would have swelled into a red giant. In this phase, it can shed enormous amounts of material. If the binary system is tight, some of this expelled gas might not escape entirely. Instead, it could settle into a stable, rotating disk that encircles both stars, a circumbinary disk, much like the rings around Saturn but on a stellar scale. This disk would be incredibly tenuous and cold, almost invisible, persisting for millions of years as the stars complete their evolution and collapse into neutron stars. It would be a fossil of the system's violent adolescence. The existence of such a disk would fundamentally change the final act. When the two neutron stars finally merge, their cataclysmic explosion would occur not in a perfect vacuum, but inside this ancient reservoir of material. The relativistic jet blasting out from the newborn black hole or magnetar would immediately plow into this disk. The interaction would be spectacular. The disk material would be violently shocked and heated, potentially creating a much brighter and longer-lasting afterglow across multiple wavelengths. The jet itself might be slowed or shaped by the disk, altering the burst's properties in ways we could measure. Even the kilonova could be affected. The expanding cloud of heavy elements would slam into this pre-existing gas, creating additional shocks and emission that could mask or modify the expected red and blue glow, making the chemical fingerprint harder to read. Yet, for all its potential consequences, conclusive evidence for such a disk remains elusive. Why is it so hard to find? The disk, if it exists, would be cold and dark for eons, emitting only faint radio or infrared radiation, a whisper lost in the background hum of the galaxy. By the time the merger happens and we train our telescopes on the site, any signal from the disk itself would be utterly overwhelmed by the brilliant flash and afterglow. We would have to infer its presence indirectly through subtle anomalies in the light curve, perhaps an afterglow that remains mysteriously bright for too long, or an unexpected color in the kilonova that points to interaction with lightweight elements like hydrogen or helium elements that should not be present in a pure neutron star merger but would be abundant in an old stellar disk. Finding these clues is a painstaking forensic process. Each short burst becomes a unique case study. Does its afterglow behave in a way that only a clean environment can explain, or does it hint at something more complex? So far, the clean model fits most observations, suggesting that if circumbinary disks exist, they are rare, or they dissipate long before the merger occurs. But their potential existence opens a fascinating narrative. It means that some of these catastrophic collisions might be waiting on a stage set billions of years earlier, their final fury amplified by the forgotten remnants of their first death. It connects the quiet, slow evolution of a binary system directly to the brilliance of its end, a hidden thread of continuity in a story defined by sudden, unimaginable violence. The silent disks of their past might be hard to see, but the most distant bursts of all could illuminate the universe's deepest past. This is the 25th mystery, the hunt for the cosmic dawn detectives. We know that the first stars in the universe were massive, blazing briefly and dying young in spectacular supernova. Those deaths should have created the first neutron stars, and some of those should have paired up and merged. Theoretically, short gamma-ray bursts should have been flashing in the darkness when the cosmos was less than 1 billion years old, during the era of the very first galaxies. These flashes would be more than just ancient cataclysms, they would be revolutionary probes. Their light, stretched by cosmic expansion into the infrared, would carry the chemical fingerprint of the early intergalactic medium. It would tell us what the universe was made of before generations of stars polluted it with heavy elements. The burst's afterglow could act as a backlight, illuminating the structure of primordial gas clouds and revealing how the first galaxies assembled. Yet, despite decades of searching, we have not definitively caught a single short burst from that primordial epoch. The record holders are still from a universe several billion years old. Their silence is a profound cosmic question mark. Were neutron star mergers simply less common in the early universe? Perhaps the first stars, often solitary giants, rarely formed in tight binary pairs necessary for a later merger. Or maybe the time delay between the birth of the stars and their final collision is almost always longer than a few billion years, meaning those first pairs are only merging now in the modern universe. There is another, more practical possibility. Their signals are simply too faint for our current telescopes to see. A short burst from the cosmic dawn would be incredibly redshifted. Its brilliant gamma-ray flash would be stretched into the X-ray or even ultraviolet part of the spectrum by the time it reaches us. Its afterglow would be shifted deep into the infrared, a part of the spectrum where our telescopes are less sensitive and the sky is filled with noise. By the time our satellites trigger an alert and more powerful infrared telescopes like the James Webb Space Telescope swing into view, that faint, ancient afterglow may have already vanished, leaving no trace. Finding one of these primordial flashes would be an archaeological triumph. It would confirm that the universe's first stellar deaths could forge these incredibly dense remnants and set them on a collision course. It would provide a direct timestamp proving that such complex astrophysical processes were underway shockingly early in cosmic history. More than that, it would give us a pristine laboratory. The environment around such an early merger would be almost purely hydrogen and helium, untainted by the products of later stellar generations. Any heavy elements we detected in its kilonova or absorption lines would have to be from the merger itself, offering a clean measurement of the R process in its most primitive form. So the search continues, a patient scan of the data from every detected burst, looking for that one whose light has traveled the farthest. Each new space telescope, with greater sensitivity to infrared and faster reaction times, brings us closer to that goal. The hope is to catch a flash from a time when the universe was in its infancy, a brief, violent beacon from the dawn of creation, holding secrets about how everything we see today began. The search for primordial bursts forces us to reconstruct the cataclysm itself, piece by ejected piece. The most dramatic of these pieces are not the jets, but the vast plumes of star stuff ripped out by gravity before the final impact. When two neutron stars enter their last frantic orbits, their gravitational pull on each other becomes monstrous. They stretch and distort one another, pulling long, spiraling streams of ultra-dense material out from their surfaces. These are the tidal tails, and their fate is the 26th mystery. They represent a significant fraction of the total mass involved, and what happens to this material in the milliseconds following the collision can dictate the entire character of the explosion. Imagine two spheres of honey spinning around each other at impossible speeds. Just before they slam together, their shapes distort, throwing out long, sticky threads. In the cosmic version, these threads are made of neutron-rich matter, and they are flung out at velocities that are a significant fraction of light speed. But they are not necessarily free. Their destiny hangs in a delicate balance between escape and recapture. A portion of this tidal debris flung furthest out may achieve escape velocity. It becomes the primary source of the kilonova ejector, the cloud that will glow with the radioactive decay of newly forged gold and platinum. This material is launched on a one-way trip into interstellar space, destined to enrich future generations of stars and planets. Yet another portion of the tidal tails might follow a different, more violent path. These streams are launched on shallower trajectories, like a fountain that arcs up only to fall back down. In the chaotic gravity of the newborn remnant, whether it is a hypermassive neutron star or a fledgling black hole, this material can rain back down onto the central engine. This fallback accretion is a potential second course of fuel. It could provide a sustained energy source, powering an extended emission or a plateau in the X-ray afterglow long after the initial jet has subsided. In essence, the collision might not be a single, instantaneous detonation, but a two-stage event, the first from the immediate merger and the second from the delayed feast of its own debris. The balance between these two fates, escape or fallback, is a critical unknown. It depends on extremely fine details, the exact masses of the neutron stars, their spins, the stiffness of their internal matter, and the precise angle of their collision. A more asymmetric merger might fling more material out permanently, creating a brighter kilonova but leaving less fuel for the central engine, potentially resulting in a weaker gamma-ray burst. A more symmetric, head-on collision might produce less ejector but more efficient fallback, leading to a more powerful and sustained central engine. This is why modeling these events is so fiendishly difficult. Supercomputers run for months simulating those final milliseconds, trying to track every stream of particles to see where it goes. The light we eventually see is the sum total of all these chaotic processes. Observing this dynamic is nearly impossible directly, but its consequences are written in the light curves. A kilonova that is unusually bright or evolves in an unexpected way might signal an especially large tidal tail ejection. An X-ray afterglow with a peculiar re-brightening days later could be the signature of delayed fallback material finally crashing onto the remnant. Each short gamma-ray burst, therefore, gives us a different experiment in tidal physics. By comparing the brightness and timing of the gamma-ray flash, the X-ray afterglow, and the kilonova, astronomers can work backwards to estimate how much mass was ejected and how much fell back. The tidal tails are the missing link, the connective tissue between the gravitational wave chirp of the in-spiral and the brilliant electromagnetic display that follows. They are the treasure spilled from the collision, and whether that treasure is lost to the void or reclaimed by the monster at the center determines the final legacy of the most violent embrace in the cosmos. The fate of those tidal tails is shaped by a force even more primal than gravity. The merger environment is a cauldron of magnetism, a place where the universe's most powerful magnetic fields are born. In the milliseconds it takes for two neutron stars to become one, magnetic fields can be amplified from an already staggering strength to levels that defy comprehension, reaching intensities trillions of times greater than Earth's protective field. This explosive growth is the 27th mystery, a process so chaotic and fast that even our most powerful supercomputers can only glimpse its outline. How does this magnetic storm ignite, and how does it seize control of the explosion to forge and direct the lethal jet? The seeds of the storm are already there. Each neutron star possesses its own incredibly powerful magnetic field, frozen into its super-dense material from the star's violent birth. As the stars spiral in for their final embrace, these fields are dragged along, twisted and stretched by the insane orbital motion. When the stars finally make contact, it is not a gentle meeting. Their outer layers shred and mingle, creating a turbulent, hyper-hot soup of particles and magnetic field lines. This is where the true amplification begins, through a mechanism called the magnetorotational instability. Imagine you have two fluids, one spinning faster than the other, and they are laced with magnetic fields. The shear between them, the difference in their rotational speeds, acts like a dynamo. It stretches the magnetic field lines, winding them tighter and tighter, converting the raw kinetic energy of the spinning wreckage directly into magnetic energy. The process feeds on itself, a runaway reaction where a stronger field creates more turbulence, which in turn amplifies the field further. In a literal flash, the magnetic energy density can surpass the thermal energy of the plasma itself, becoming the dominant force in the room. This magnetic maelstrom is the unseen architect of the jet. The field does not just grow, it organizes. The chaotic turbulence begins to smooth out, and the amplified fields line up along the axis of rotation of the remnant, like the orderly lines of force around a bar magnet. This creates a magnetic funnel, a channel of unimaginable power extending from the poles of the hypermassive star or the swirling accretion disk. It is within this funnel that the jet is born. The magnetic field acts as both a particle accelerator and a railgun. It grabs hold of charged particles in the hot plasma and flings them outward along these polar lines, accelerating them to nearly the speed of light. The field also provides the collimation, the tight focusing that keeps the jet from spreading out into a useless spray. It squeezes the energetic particles into a narrow beam, a cosmic laser of matter and radiation. Without this magnetic focusing, the energy of the merger would dissipate in all directions, and we would never see the brilliant, focused flash of a gamma-ray burst. The mystery lies in the details our simulations cannot yet capture. The magnetohydrodynamics, the complex dance between magnetic fields and fluid motion at relativistic speeds, is a nightmare to model. The scales involved range from the kilometers of the merging stars down to the microscopic gyrations of individual particles. Our computers must make simplifying assumptions, and we fear that in doing so, they are missing the true, chaotic essence of the process. Does the magnetic field amplify in a smooth, global fashion or in violent, localized knots? How much of the system's rotational energy does it actually manage to tap and convert into the jet? The answers are locked inside that millisecond of creation, a storm of physics so intense it forges the universe's most focused beams of energy from pure chaos. That magnetic funnel focuses the jet into a narrow beam, but for every one aimed directly at Earth, countless others are pointed elsewhere. Their light vanishes into the cosmic dark, leaving behind only a ghost. This is the 28th mystery, the search for the short gamma-ray burst orphans. If the powerful core of the jet is aimed away from our line of sight, we miss the brilliant initial flash entirely. What we might still catch, however, is the faint, wider glow from the jet's slower-moving material as it plows into the surrounding space long after the main event. This is the orphan afterglow, a cosmic echo without its originating thunderclap. Spotting one would be like seeing the glowing wake of a ship that passed in the night, its hull never visible. The challenge is that these orphan afterglows are incredibly faint and evolve very slowly. Unlike the sharp, fast-decaying afterglow of a burst we see head-on, an orphan afterglow from an off-axis jet brightens gradually over days or weeks as more of the wider emission cone comes into our view. It is a slow-motion reveal of a catastrophe we never witnessed. Finding such a signal requires a new kind of astronomical survey. Instead of waiting for a satellite to trigger an alert, astronomers must repeatedly scan large swaths of the sky with sensitive radio and optical telescopes, looking for any new point of light that appears and brightens in an unusual way. They are searching for a needle in a haystack where the needle itself is dim and changes almost imperceptibly. Every new, unexplained transient in the sky must be scrutinized to see if its behavior matches the predicted slow rise of an orphan afterglow. The stakes for a detection are immense. First, it would directly confirm the structured jet model, proving that short bursts have a bright core surrounded by a dimmer, wider sheath. By measuring how the orphan afterglow brightens and fades, we could precisely map the jet's geometry, its opening angle, and how its energy is distributed. But the greater prize is a census of the unseen. A single detection would prove that orphan afterglows exist. From that, we could begin to estimate how many mergers are happening completely hidden from our gamma-ray telescopes. It would answer the haunting rate discrepancy, telling us if we are seeing 1 in 100 of these events or 1 in 1,000. Each orphan afterglow would be a silent witness to a collision that produced no brilliant flash for Earth, a direct count of the dark population. Yet, the universe guards this secret closely. To date, no confirmed orphan afterglow from a short burst has been found. The candidates that have appeared often have other, more mundane explanations, like a distant supernova or a flaring star in our own galaxy. The search continues, a patient, sweeping gaze across the heavens, looking for the faintest of glows from a tragedy whose main act we were never meant to see. It is a hunt for ghosts, but finding even one would illuminate the true scale of violence in the cosmos, revealing a hidden universe of collisions whose only testament is a slow, silent afterglow in the dark. The faint glow of an orphan afterglow hints at a hidden population, but our next revolution will not rely on light alone. We are entering the era of multi-messenger astronomy, where we observe the cosmos with every sense we can muster. This is the 29th mystery, the promise of a complete picture. Imagine hearing the thunderclap, feeling the wind, and seeing the lightning all from the same storm. For a neutron star merger, that means detecting the gravitational waves, the neutrinos, and the gamma-ray burst in perfect, simultaneous coincidence. Our tools are now in place. The global network of gravitational wave observatories, LIGO in the United States, Virgo in Italy, and CAGRA in Japan, listens for the faint tremors of spacetime. Neutrino telescopes like IceCube at the South Pole and KM3NT in the Mediterranean Sea watch for the arrival of ghostly particles, and a fleet of space-based observatories from Swift to Fermi scans for the brilliant flash of gamma rays. A single event that triggers all three would be the ultimate cosmic autopsy, revealing secrets no single messenger could ever provide. The gravitational wave chirp gives us the prelude, the precise masses and spins of the neutron stars in their final moments. The neutrino burst, if we can catch it, would be a direct probe of the jet's hidden engine, telling us about particle acceleration in real time. And the electromagnetic cascade from gamma rays to the kilonova's glow shows us the aftermath, the chemistry and the light. Together, they would form a single, unbroken narrative, but the true mystery lies in what discrepancies might appear. What if the gravitational waves suggest the formation of a hypermassive neutron star, but the gamma-ray burst is unusually weak, hinting at a choked jet? That mismatch could reveal how magnetic fields or the surrounding debris can stifle an explosion. Or what if the neutrino signal arrives a fraction of a second after the gravitational waves? That delay could map the exact sequence of events inside the merger, timing the launch of the jet relative to the collapse of the remnant. This multi-messenger approach would also serve as the universe's most stringent physics lab. By comparing the arrival time of gravitational waves, which travel unimpeded with the light and neutrinos, we can test Einstein's theory of general relativity with unprecedented precision. Does gravity truly travel at the speed of light, even across billions of light years? Any tiny deviation would shake the foundations of physics. Furthermore, the kilonova's light would give us the chemical output of the R process, while the gravitational waves would tell us the masses that went into that nuclear cauldron. This would finally allow us to calibrate the cosmic recipe for heavy elements, linking specific progenitor masses to the amounts of gold and platinum they forge. We are on the cusp of this future. Every observing run of the gravitational wave detectors brings a higher chance of catching another neutron star merger. Astronomers and physicists worldwide maintain a state of constant readiness, their alert systems intricately linked, poised for the moment the universe sends a signal through all three channels at once. That moment will transform these fleeting mysteries from puzzles into data points, weaving a complete story from the ripples in space-time, the whispers of ghosts, and the most brilliant light in the cosmos. It promises to turn a single second of violence into a lifetime of understanding. The final, lingering question is what the universe builds from the wreckage. After the jets fade and the kilonova cools, a single, compact object remains at the heart of the cataclysm. Its nature is the 30th and ultimate mystery, a secret that dictates the long-term legacy of the entire event. We are left with three profound possibilities, each rewriting the laws of physics in its own way. The first is the black hole, the silent conqueror. This is the simplest outcome, a bottomless pit in space-time where the combined mass of two stars vanishes from our universe, leaving behind only its gravity. The second is the magnetar, the magnetic phoenix. This is a neutron star born with a magnetic field of apocalyptic strength, spinning hundreds of times per second, raging against its own inevitable decay. The third is the most exotic of all, a theoretical object that has never been confirmed, a quark star. Imagine the pressure of the collapse is so immense it breaks down the very neutrons themselves, crushing them into a soup of their fundamental constituents, quarks. This would be a state of matter not seen since the first microseconds after the Big Bang, a perfectly smooth, ultra-dense sphere existing in a realm beyond our current physics. Distinguishing between these fates from billions of light years away is a detective story written in X-rays. A newborn black hole with no solid surface and only a faint accretion disk offers little to see. Once its initial feast is over, it goes dark, a silent monarch in an empty throne room. Its presence is inferred only by the absence of any other signal. A magnetar, however, is a lighthouse. It spins down over time, converting its immense rotational energy into a powerful wind of particles and radiation. This wind can continuously inject energy into the expanding shell of the kilonova or the remnants of the jet, creating a sustained glow. This is the fingerprint astronomers search for in the long-term afterglow. If the X-ray emission from a burst site plateaus for hours or even days, refusing to fade, it is a strong hint that a central engine is still active, still pumping energy into the system. That engine is likely a spinning magnetar, slowly winding down like a cosmic top, but the signal must be passed with extreme care. Could that same plateau be produced by a black hole with a particularly long-lived disk of debris? Perhaps the true smoking gun would be the detection of a rhythmic pulse, the X-ray heartbeat of the spinning magnetar itself. Finding that faint, periodic flicker buried in the noisy data from a distant galaxy is perhaps the greatest observational challenge in this field. It would be a direct image of the remnant's beating heart. Meanwhile, evidence for a quark star would be even subtler. Its predicted properties sit in a strange middle ground. It might cool faster than a neutron star, or have a different pattern of vibrations imprinted on the gravitational wave signal of the merger itself. A single, definitive observation would revolutionize our understanding of matter itself, proving that neutrons are not the final word in density, that there is a stage of collapse even more extreme. So the aftermath of the universe's most brilliant flash is a long, quiet vigil. Astronomers point the most sensitive X-ray telescopes, like Chandra and XMM Newton, at the coordinates of old bursts, sometimes months or years later, listening for a whisper. They are waiting to hear if the remnant is a silent sovereign, a furious dynamo, or a completely new kingdom of matter. The answer does more than close a chapter. It tells us the final state of matter pushed beyond all limits. It reveals whether the collision of two dead stars always creates an abyss, or if sometimes, against all odds, it forges a new kind of star to light the cosmic dark, however briefly. In that quiet, enduring glow, the last secret of the short gamma-ray burst is waiting to be told. These 30 mysteries are not just a catalogue of cosmic oddities. They are the fundamental questions written in the most brilliant ink the universe possesses. In a flash lasting less time than a heartbeat, a short gamma-ray burst compresses the extremes of physics into a single, observable moment. It is a cosmic Rosetta Stone, a singular event where gravity, nuclear physics, magnetism, and quantum mechanics all collide, leaving behind a cipher we are only beginning to decode. Every mystery we solve, from the faintness of an afterglow to the color of a kilonova, is a key turning in a lock. It reveals not just the fate of two dead stars, but the strength of space-time, the recipe for gold, and the hidden history of galaxies. These fleeting flashes illuminate the darkest corners of physics, from the event horizon of a newborn black hole to the quantum foam of the vacuum itself. Their story is a reminder that the universe hides its grandest truths in its most transient events. So keep looking up and keep wondering. The next great flash could arrive at any second, carrying with it the answer to a mystery we have not even thought to ask yet. Which of these 30 puzzles leaves you the most awestruck? Share your thoughts below and subscribe to join us as we unravel the next great cosmic secret.